Hello. Welcome to an adventure. I hope that you can hear me. I think that you can. I hope that you can hear the music. I think that you can hear that as well. If either of those thoughts of mine are incorrect, do let me know. Also, I hope you're just having a great Wednesday. I know I said also like I had some big important thing to say, but I didn't. I was just, hi. I'm so happy that you're joining me today. And hello Key Squared and hello Hannah, it's good to see you. Confirming music and sound from me. Excellent. It is really, really warm in here. I have a fan on. It does have one higher setting that I could put it to, and that may end up happening. But under all these lights, the 74 degrees with 50% humidity that the thermometer says feels a lot warmer. Anyway, fun fact, the latest accelerator project at Brookhaven, where the Cosmotron was built, is an electron ion collider. Brookhaven's design won the competition over the other candidate, which would have been at Newport News, Virginia. Awesome. Thank you for sharing that, Key Squared. Yes, today we're going to be looking at some stuff related to the Cosmotron, which was an accelerator. That's all I know, particle accelerator. I don't know any more specifics than that. I assume that we will learn as part of today. But in order to get started on that, we should dive into our normal, thank you, Hannah, acknowledgement thing here. The Virginia Tech Land Acknowledgement and Labor Recognition. We cover these at the top of every archives stream since we are dealing with historic information and historical materials. I think it's good to pay attention to the university's statements here regarding their own past. Virginia Tech acknowledges that we live and work on the Tudelo and Monacan people's homeland, and we recognize their continued relationships with their lands and waterways. We further acknowledge that the Morrill Land Grant College Act of 1862 enabled the Commonwealth of Virginia to finance and found Virginia Tech through the forced removal of Native nations from their lands in Western territories. We understand that honoring Native peoples without explicit material commitments falls short of our institutional responsibilities. Through sustained, transparent, and meaningful engagement with the Tudelo and Monacan peoples and other Native nations, we commit to changing the trajectory of Virginia Tech's history by increasing Indigenous student, staff, and faculty recruitment and retention, diversifying course offerings, and meeting the growing needs of all Virginia tribes and supporting their sovereignty. Virginia Tech acknowledges that its Blacksburg campus sits partly on land that was previously the site of the Smithfield and Solitude plantations, owned by members of the Preston family. Between the 1770s and the 1860s, the Prestons and other local white families that owned parcels of what became Virginia Tech also owned hundreds of enslaved people. We acknowledge that enslaved black people generated wealth that financed the predecessor institution to Virginia Tech, the Preston and Olin Institute, and they also worked on construction of its building. Not until 1953, however, was the first black student permitted to enroll. Through inclusive VT, the institutional and individual commitment to prosim that I may serve, in the spirit of community, diversity, and excellence, we commit to advancing a more diverse, equitable, and inclusive community. So we just like to take a look at that and remind ourselves that we can do better at the top of these streams, and especially important because often we encounter things that aren't great. All right. Let me make sure I am set for that. Go. And so, what we're looking at today, the George Collins papers covering 1952 to 1993 Thank you again, Hannah. The finding aid there in the chat. If you click the link, it'll take you to this page on the archival resources of the Virginias, where you can learn a little bit about this collection, about who is George Collins, why did I name this Collins Cosmotron Correspondence, you know, that sort of thing. So we've got a total of 2 cubic feet, 3 boxes, 1 oversized folder, short description. These papers are comprised mostly of correspondence from George B. Collins's time as chairman of the Brookhaven's Cosmotron Department. The Brookhaven Institute's, or Brookhaven Labs Cosmotron Department, not the Brookhavens, but okay, you know, some grammatical issue there. Hi, Concilians, welcome. Thank you for the resubscription. 26 months. Excellent. It's good to see you. The collection also contains travel vouchers, research proposals, travel reports, and materials relating to Collins' work as a professor at the University of Notre Dame and at Virginia Tech. I guess it's technically Notre Dame. But my brain read it Notre Dame. But it is definitely Notre Dame. Let's see. So who is this George Collins person? George Collins, a physicist, particle experimentalist, educator, and administrator, earned a PhD with R.W. Hood at Hopkins, studying UV spectroscopy. Incidentally, if anybody can tell me who R.W. Wood is, I'd appreciate it, because the way it is mentioned here, it seems like a person that I should know, and I don't. So if anybody does know and wants to drop that in chat, please do so. And if not, we'll return to that and try and figure out, because I have no knowledge. Collins was a professor at Notre Dame working on nuclear excitation and disintegration. He was responsible for the construction of a nuclear accelerator for the Notre Dame Nuclear Physics Lab in 1935. He worked with Dr. Jose Caparo. In 1935, the accelerator was Notre Dame's largest nuclear physics-related project to that date. The accelerator was the source of several decades' research on nuclear physics, much of which was headed by Collins. At MIT, he assisted the war effort in the radiation laboratory, developing radar for military purposes. He taught at the University of Rochester and served the Department of Physics as chairman. He was in charge of construction and operation of the 240 megavolt synchrocyclotron and initiated, with Robert Marshak, the Rochester conferences. He was chairman of Brookhaven's Cosmotron Department and a Fulbright Fellow in Belgium. Late in his career, he came to Virginia Tech and taught physics from 1968 to 1976. So, I have the whole collection here. Despite the title saying Cosmotron Correspondence, we do not have to limit ourselves to Series 1. If there are other things that you want to see, do let me know, because I do have all of them here and we can look at any of them. Robert Williams Wood was an American physicist and inventor who made pivotal contributions to the field of optics. He pioneered infrared and ultraviolet photography. Wood's patents and theoretical work inform modern understanding of the physics of ultraviolet light, and made possible myriad uses of UV fluorescence, which became popular after World War I. He published many articles on spectroscopy, phosphorescence, diffraction, and ultraviolet light. Awesome. Thank you, Hannah, for locating that information. Because yeah, I was like, I don't know. Just add Notre Dame to the list of things that Americans pronounce wrong. Yep. We've mentioned this before. I remember on a stream observing like the pronunciation of Cairo, Illinois. Was it Cairo? Yeah, that's Illinois, isn't it? I don't know. Cairo. There's a place out in the Midwest called Cairo, spelled Cairo. Anyway, we've definitely had that discussion before. Anyway, so yes, if you want to look through the finding aid, Series 1 is Correspondence, and it's literally just broken down by year. So I'm fine reading people's mail, but if there's stuff in the Series 2 papers that sounds interesting to you, or anything in the artifacts area that sounds interesting to you, do let me know, because I'm fine also looking at that. The photograph, I may actually start with the photograph, because I think it's good to sort of get that image at the beginning. But yeah, how about we explore and see what we can find? Yeah? Buttons pushed. Okay. Box 3. If I want the photograph, I need box 3. Box 3 is a flat box. Oh, and it's a framed photograph, it looks like. Also, while we're here, notice the rule against smoking and open flames on the Cosmotron floor will be enforced when signs are erected. GB Collins. So it will be enforced, but only when the signs are up. I love the qualification there. Is this sign a sign? A sign of what? Let me see if I can zoom in a little bit here. Because this is a framed... it's a framed photograph from a newspaper, which is unusual. Times Union. I do not know where the Times Union is from. I'm just going to see. There's a Times Union in Albany, New York. Where is the Cosmotron? I suppose that is and Key Squared is like Albany. Brookhaven is in New York. Okay, so the Albany Times Union would make sense then. I knew it was at Brookhaven, but like, I honestly have not looked to see where Brookhaven was located. Trying to keep with the theme of I basically know nothing about the materials we're about to look at. So, all right, 5 individuals here. We have A. Salam, native of India, now a research physicist in England, working at the University of Cambridge, one of several Indians at UR conference. University of Rochester conference. Like, I knew the R was Rochester, I was trying to figure out what the U was, but it's the University of Rochester conference. Robert F. Bacher, California Institute of Technology, professor, former head of experimental physics at Los Alamos, New Mexico. Isidore Raby, Columbia University Nobel Prize winner, helped prepare agenda for first worldwide conference on peaceful use of atomic energy. These are people that we have looked at materials about or referencing them in previous installments of the High Energy Physics series. George B. Collins, former University of Rochester physics chairman, now head of accelerator research at Brookhaven National Laboratory, Long Island. I see. Okay, so Brookhaven's on Long Island. And W.M. Powell, head of cloud chamber research at the world's largest atom smasher, the Bevatron at the University of California, Berkeley. I don't think I had heard of the Bevatron before. The Cosmotron I had definitely heard of. It's the first time I've heard the Bevatron mentioned. Brookhaven's in New York. It's on Long Island, not very close to Albany. That's true, but yeah. I appreciate that Collins is the only one in a bow tie. So yeah, I'm glad that we actually got a photo of Collins in choosing to go to the photographs first, because I think it's helpful to have seen the person. All right, I'm gonna pop open box 1, and box 1 is series 1 essentially, and so we got a bunch of dead people's mail, which sometimes that's what archives are, is a bunch of dead people's mail, and I get to read their mail, which can be fun. It can be boring, but it can also be fun. So starting in 1952, let's find out what we got. The first thing in here actually is not a letter. It is Brookhaven National Laboratory, Cosmotron Dedication, December 15th, 1952. United States Atomic Energy Commission and Associated Universities Incorporated. Yeah. At first I was trying to figure out if the mathematical calculations on the front were part of the illustration or not. They are not. And I only know that because they're on top of the letters in the title. If they were part of the illustration, I would expect them to be behind those letters. So it looks like somebody was calculating sums on the front of this with a piece of chalk, it looks like. Anyway. Brookhaven National Laboratory. Objectives and organization. Ooh. I don't think I have looked at these before. Regional Research Center for Fundamental and Applied Research in the Nuclear Sciences and Related Subjects, and an integral part of the Atomic Energy Commission's nationwide program. 4 objectives. Seek new knowledge in the nuclear and other related sciences. Encourage appropriate use of its facilities by qualified scientists of university and other laboratories, primarily in the Northeast. Assist the Atomic Energy Commission in the solution of specific problems. Aid in the training of scientists and engineers in nuclear science and technology. The laboratory was established as a cooperative post-war venture in recognition of the necessity for large and expansive equipments and concentrations of scientific manpower for the successful prosecution of nuclear research. Like other national laboratories of the Commission, Brookhaven is operated under contract by a private institution, in this case Associated Universities Incorporated. This nonprofit educational corporation serves as an agency through which universities and other institutions can cooperate with one another and with the government to further research and education. The governing body of the corporation and board of trustees, blah, 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 blah. Let's see. 9 sponsoring universities: Columbia, Cornell, Harvard, Johns Hopkins, MIT, Princeton, University of Pennsylvania, University of Rochester, and Yale. Cool. Ooh, we get pictures. I'm happy that we get some pictures. Let's see, above, loading face of the Brookhaven reactor, aluminum cartridges containing uranium are inserted through the holes into the graphite moderator. And left, the west face of the reactor, on the ground level and on the first 2 balconies are located equipment for experiments with beams of neutrons from the reactor. Interesting. On the ground and the first 2 balconies. Cooperation in the scientific work is carried out in a variety of ways through participation in the Brookhaven program by visiting scientists on leave from other institutions or pursuing research toward a graduate degree, collaborative projects with other institutions, and through the use of the major facilities by others for research not directly connected with the laboratory programs. Finally, in accordance with the Commission's overall program, Brookhaven produces and sells radioisotopes and irradiates materials for others in its reactor. Aha! Looks like they had in 1952, they had a staff of 1,400. 300 were scientists, 500 technical and skilled personnel, 600 support staff. And so scientific facilities, they had nuclear reactor, accelerators, and other facilities. Let's see. So I'm going to look at the accelerators. In other machines called accelerators, beams made up of high speed and hence high energy charged particles are produced by accelerating the particles in electric fields. An electrostatic accelerator at Brookhaven produces potentials up to 2.5 million volts by electromechanical means inside a large steel tank. Protons and deuterons, thus accelerated, are used for very accurate experiments on nuclear structure in the hope that more can be learned about the laws governing the interaction of many particles in a single nucleus. Can someone remind me what deuterons are? I know protons are subatomic particles with a positive charge, but I don't remember what deuterons are. In the second type of accelerator, called a cyclotron, particles are speeded up to much higher energies by repeatedly passing them through an electric field as they spiral outward in the field between the poles of a large electromagnet. One such instrument at Brookhaven, with a pole diameter of 60 inches, produces 20 million volt deuterons, which are of great value in physics, chemistry, biology, and medicine. It is used to extend the work of the electrostatic accelerator to higher, though less precise, energies, to produce neutrons for certain special experiments, and to manufacture radioactive isotopes not available from the reactor. Deuterons. Heavy hydrogen nucleus, a neutron-proton pair is a deuteron. Awesome, thank you. Hi, Puddleglum. Welcome, it's good to see you. The most unusual and most exciting accelerator is the Cosmotron, a proton synchrotron which accelerates particles up to energies of 2.3 to 3 billion electron volts. A more detailed description appears further on in this booklet. I just love that everything is Tron. Not the movie from like the 80s that you get digitized and end up on the grid inside of a computer. Not that Tron, but all of these Trons, the cyclotron and the Cosmotron, and everything is Tron. Let's see. The research program proper, as distinct from the facilities, may be summarized under 4 general headings: studies of atomic nuclei, effects of radiation upon matter, radioisotopes and other nuclear tools, and nuclear technology. Incidentally, none of these materials, at least to my knowledge, are in any way radioactive. I don't know that we would have tested, but they've been sitting near my desk for quite a while now, and I haven't had any negative effects. Mutations and other changes in plants are induced by exposure to gamma rays emitted by radioactive cobalt in the center of this field. Huh. Interesting. I feel like some of these radioactive isotopes have to occur naturally in the environment, right? Otherwise, how would we ever have discovered them? Well, I mean, experiment. But anyway, I'm imagining a Monty Python-esque skit with Vikings singing Tron, 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 Tron. Oh, that would be, yeah, okay. That would be good. This is a picture of the cyclotron. This is an amazing photo. This is the photo I picked for like the cover of the graphic for today's stream, because that's a really cool photo. I do not know who took the photographs for this. Also, there's no caption for this photo. The Cosmotron. Or Cosmotron, that's, of course, yes, the Cosmotron. Did I say cyclotron? I meant Cosmotron. They're 2 different machines, both at Brookhaven. The nuclei of atoms are composed of neutrons and protons, 2 particles which until recently seemed to be elementary and without structure. Remember, this is 1952 science. Experiments with cosmic rays have now shown, however, that neutrons and protons are themselves complex entities. There is thus revealed a hitherto unsuspected new and important field for physical research, which seems fundamental to all nuclear physics. The complexity of neutrons and protons is evident only when these particles collide with an energy of hundreds of millions of electron volts or more. Such collisions frequently result in the production of short-lived particles called mesons, or mesons, which may be the key to the understanding of the nature of nuclear forces. At least 5 varieties of mesons have now been observed in experiments utilizing cosmic rays. Precise experiments with cosmic rays are very difficult to perform because the incoming particles have a wide range of energy and are of feeble intensity. It is thus highly desirable to provide an intense laboratory-controlled source of ultra-high energy particles. Heretofore, the highest energy sources have been large cyclotrons, accelerating protons to almost 500 million electron volts, near the feasible economic limit for such machines because of the tremendous amounts of iron required in their massive magnets. The Brookhaven Cosmotron was designed to utilize new techniques in extending the available energies to 2.5 billion electron volts or more. The basis of the Cosmotron, technically a proton synchrotron, is an electromagnet, 75 feet in diameter. I don't know why I read meters. Which guides the protons in a circular path while they are being accelerated to higher and higher energies by repetitive application of an electric field synchronized with their motion. Unlike the cyclotron, in which the particles spiral outward in a constant magnetic field between solid cylindrical poles as their energy increases, the Cosmotron has a ring-shaped and hence more economical magnet, in which the spiraling tendency is overcome by increasing the field during the acceleration period. During this time, the protons which were injected into the Cosmotron from a 4 million volt electrostatic accelerator gain energy at a rate of approximately 800 electron volts per revolution. At the end of 1 second, they have circled the magnet some 3 million times and have acquired a total energy of the order of 2.3 billion electron volts. Their total path of more than 150,000 miles would be quite impossible of achievement were it not for the focusing properties of the magnet and the very high vacuum obtained within the ring-shaped accelerating tube. And the image there is a photomicrograph of the first photographic emulsion exposed to 2 billion volt nuclear particles in the Cosmotron. The nucleus of an atom of the emulsion was hit by a particle, exploding the nucleus into 17 different visible particles, which flew out, forming tracks in this star-shaped pattern. Usually they occur in nature diluted with a bunch of less active isotopes. You have to refine them a lot to get anything exciting, which is a good thing, obviously. Yes, okay. That is, yeah, like I knew like there had to be radioactive isotopes in nature, but then I was missing the whole, of course, you refine them. And I should know this because like refining enough, say like, well, if you look at like the Manhattan Project, refining enough U-235 to sustain the reaction necessary for the bomb to work was difficult. Let's see. Right here. Inside the laminated 12-ton magnet is a dome-shaped cloud chamber, 16 inches in diameter. The chamber was designed for studies of nuclear particles produced by the Cosmotron. Interesting. Oh, there's some history of the Cosmotron. We'll read that in a second. Below, first cloud chamber photograph showing high-energy particles resulting from single pulse of 1.2 billion electron volt protons striking a brass target inside the Cosmotron. The chamber was located 195 feet from the target. Let's see. After the protons have reached the desired energy, they are allowed to strike a target. The magnet is then turned off and the entire process is repeated 4 seconds later so that brief bursts of protons are delivered to the target at 5-second intervals. Particles such as neutrons, mesons, and gamma rays, which result from the target bombardment, may be observed with nearby photographic films or other small experiments, or other small equipments, or may pass through channels in a massive concrete shield into a large experimental area. In the latter is located the bulk of the experimental equipment, including cloud chambers, counters, and films for observing the particles. Experiments will include measurements both of the fundamental properties of the particles and of their interactions with secondary targets. It is hoped that ultimately the protons themselves can be led out of the Cosmotron so that the primary target can be located in the experimental area. Among the equipments now in operation are 2 large cloud chambers. One is provided with a strong magnetic field for determining the masses of particles by observing their deflections. The others made very long in order to give long trajectories for observing infrequent collisions of the high-energy particles with the gas in the chamber. Among the secondary targets will soon be one of liquid hydrogen, important because the nuclei of its atoms are simple protons, so that the observable interactions will be both significant and as simple as possible of interpretation. That sounds dangerous. Among the important experiments utilizing this target will be the measurement of the absorption of high-energy mesons, which may reveal something about the inner structure of the proton. Intensive design of the Cosmotron was initiated in the spring of 1948, first operated successfully in the spring of 1952, achieving 1.3 billion electron volts on May 20th and 2.3 billion on June 10th. The successful completion of an accelerator of this size and complexity would have been impossible without the diligent and devoted efforts of everyone concerned. I kind of wish we had correspondence from before 1952, if 1952 is when they first got it working. And all of our correspondence that we have in this collection is from 1952 onward. But anyway, ooh, this is an interesting graphic. This is 1952 high-quality infographic. The Cosmotron. How it works. 1. Injection of protons. Protons from electrostatic generator shot into metal vacuum tank of the Cosmotron at an energy of 3.6 million electron volts. 2. Revolution in magnetic field. Increasing magnetic field causes protons to spiral in around Cosmotron, making 350,000 turns per second. I think I would get dizzy. 3. Alternating voltage turned on to accelerate some protons. Accelerating voltage. Other protons which are out of step and have been slowed down by the voltage spiral in, strike the inside wall, and are lost. Amplifier produces accelerating and decelerating voltage across gap of vacuum chamber, causing about 1/2 the protons to speed up and the other half to slow down. The protons that have been speeded up by the accelerating voltage stop spiraling in, group together in a sausage-shaped bundle, and continue to revolve at higher and higher speeds. In a sausage-shaped bundle. Interesting. How do they determine that? Like, how do they know it's shaped like a sausage? I'm very curious about, like, because this is all too small to observe with your eyes. So how do they know? I'm sure they have some sort of sensing equipment that I don't know. 4. Protons accelerated to about 175,000 miles per second, or 90% of the speed of light. Protons are now revolving at 4 million times per second, and are continually shifting their positions from one end of the bundle to the other. Sausage-shaped bundle of protons becomes smaller in diameter. Each passage through accelerating voltage adds 800 electron volts of energy to the protons. After about 3 million turns, the equivalent of 4 trips around the Earth, these protons have acquired the energy of 2.3 billion electron volts. Target inserted in path of protons. Target inserted rapidly to eventually intersect all circulating protons. These particles have lost their charge as a result of hitting target, thus becoming neutrons. They then proceed out of magnet in straight line and impact the detecting instrument, because once they're neutrons, they don't have a charge anymore, so the magnet doesn't really affect them anymore, right? Detecting instruments such as cloud chambers are used by scientists to study result of collision of these neutrons and other particles with various elements. Cool. This is really cool. Also, just like, this is just neat. This booklet. I'm glad that I started with this, because it gives me a good overview. Then you've got the Cosmotron staff here. I'm trying to find the name of the George Collins right here, just in there among the physicists. Not like called out for being the one in charge of the whole frickin' project. He's just in there listed among the physicists. I'm looking. There are other names in here that seem familiar to me. I would be really curious to like research and see how many of these people I've heard. I know we've seen Harold Pfeiffer's name before, up under mechanical engineers. But I feel like I recognize Emil Bernatsky, and I don't know why. That's somebody that's just listed down under technicians. Anyway. I see these names and I'm just like, I want to know more about all these people. With you explaining the science, my mind went to thinking about describing planets you found in Mass Effect when mining for EZO. Yeah, well, it is, I did somewhat similar there. Reading the information, the pseudoscientific information there, whereas this is like actual, like real history stuff, but yeah, kind of similar. Johns Hopkins University, Department of Physics, Homewood Campus, Baltimore, 18, Maryland. May 27th, 1952. This is a letter to George Collins from none other than Robert Wood, who we were just discussing earlier because his name showed up in the finding aid and I didn't know who he was. What? Mass Effect relays aren't real? I know. I mean, well, I can't say they're not real. I can just say that to date, we have not discovered any Mass Effect relays or Element Zero. That doesn't mean they don't exist. It's very hard to prove a negative. In fact, I believe it's impossible to prove a negative. You can, at best, say that all evidence to date says that it's not possible. Myrtle Hildred Blewett on that list was one of the few women working in accelerator physics at the time and founded a scholarship to get more women in the field. Amazing! I wonder if there's more in this collection from her. I wonder who has her papers. Probably somebody, like, I would have to follow her career. Wherever she retired from or was last is probably the place that has her papers. Just like we were the last place Collins was, which is why we have his papers. Dear Collins, your letter for my semi-centennial is the first one that I am answering. There are nearly 100 all bound in a book of red morocco and gold. I am going to answer Einstein's next, as it extremely short, but very, very nice. What a shame that we have never made contact before. I was working with Buckingham at the Western Union Lab when he was first developing the concentrated ore. The concentrated ore would be the U-235, right? Or is that arc? I can't tell if that's ore or arc. No, that's definitely arc. I don't know what the concentrated arc is. Let's see. And in my barn laboratory, when I was operating my 40-foot spectrograph, the Mercury telescope, and other amusing things, my son-in-law and married daughter knew one of the men at Brookhaven, top man on the Department of Personnel, I believe. And they got me passed 2 years ago for everything except the monster building, and said they could pass me for that, but that it would take 6 weeks to get the papers prepared and passed, and let the thing go. I was working with Dunning when we were preparing U-235 with diffusing screens made by diffraction gratings. Believe it or not, but we actually made a small quantity of pretty good stuff. Yuri, as chairman of the Manhattan Project, was trying to have the government stop our funds and adopt his centrifugal separators. That got him in wrong with Department of Chemistry of Columbia, and he was passed on to Chicago. Before this had happened, however, he took possession of Dunning's big office and conference room in the Manhattan Laboratories, which occupied a full block up on 125th Street. Yep, if I remember rightly, where I had access to every room, I think. Dunning, he transferred to a small room down the hall, the SOB. Have you by chance read Seabrook's biography of me, which is amusing, but very annoying to me in many spots? Harcourt and Brace did not make a success of it. Dr. Wood, modern wizard of the lab, two row between Harcourt or his son. What? Between Harcourt or his son with Brace resulted in the resignation of both? Just as the book was going to press. Oh, maybe it's row? To row between Harcourt or his son with Brace resulted in the resignation of both, just as the book was going to press. Yeah, definitely row, as in argument or fight. Harcourt had told Seabrook, it's just a gossip letter, all about all of these physicists that worked on the Manhattan Project. Oh, amazing. Harcourt had told Seabrook that he was going to town on it, but not until many things had to be taken out. He had been calling me bozo all through the book. He would say, now this bozo of mine, for example, at the end, he fought furiously to be allowed one bozo, but nothing doing. I could find only 3 reprints of your article in the Physics Review. It is evidently all that I had, as I never gave more than a few away of any of them, and I have a large bookcase with glass doors filled with envelopes labeled with the titles of years of reprints contained in them. Your three were loose between fat envelopes of proper date. What sort of spectroscope did you use? It is not figured, and I can't believe that I stole your carefully adjusted prisms and did not know your name for 2 years. I suppose we will get to East Hampton about June 10th. Why did you never even telephone me? Or had you forgotten my name? We've got to do something about this. Sincerely, R.W. to my close friends. And after the address, I'm just over a mild cardiac thrombus. I'm guessing cardiac thrombosis, but it says thrombus, which kept me in bed 6 weeks. Practically no pain at any time, but a bore. I've been up and dressed 2 weeks. This is my first letter. It's just gossip. The whole thing is gossip. It's fluff. It's nothing. I'm gonna answer Einstein's letter next. Woohoo! Well, goody for you, but also amazing. Okay, so what is this concentrated arc? Let's see what I can find out. A concentrated arc lamp? Please explain. Concentrated arc. No, I need more general than that. So, during the war, a new type of light source was developed under a contract issued through the Optics Division of the National Defense Research Committee. The new lamp, called the concentrated arc lamp, is basically a direct current arc lamp made with permanent fixed electrodes which are sealed into a glass bulb filled with an inert gas. The name concentrated arc comes from a characteristic of the lamp which makes it possible to concentrate the arc activity upon a small portion of the electrode so as to produce a very high-intensity light source in the form of a luminous circular spot, which is fixed in position, sharply defined, and uniformly brilliant. Okay, so that's just literally just like the incandescent bulbs that most of us grew up with. I had thought that they were older. They were developed during World War II? I had no idea. Huh. Who knew? I didn't. I thought that incandescent bulbs that have gone out of fashion in favor of first CFLs and then LEDs, but the incandescent bulb, that we grew up with, I thought was older, or that I grew up with, I thought was older. There were light bulbs, but they weren't the specific style of concentrated arc lamp. Interesting. Let's see. 8 November 1955, Sloan Physics Laboratory, Yale University, New Haven, Connecticut. That sounds off? You think they're older than that? I would be very interested. I was trying to find just like a general overview of the arc lamp, the concentrated arc lamp, but finding a generic overall description, not, okay, I am now searching for history of the incandescent light bulb. Ooh, the Department of Energy has a page called The History of the Light Bulb. Let's find out. Let's find out together even. Because now I'm curious and I need to know. All right, energy.gov, the history of the light bulb. They have broken photos, but it's okay. More than 150 years ago, inventors began working on a bright idea that would have a dramatic impact on how we use energy in our homes and offices. This invention changed the way we design buildings, increased the length of the average workday, and jump-started new businesses. It also led to new energy breakthroughs from power plants and electric transmission lines to home appliances and electric motors. Like all great inventions, the light bulb can't be credited to one inventor. It was a series of small improvements on the ideas of previous inventors that have led to the light bulbs we use in our homes today. Long before Thomas Edison patented first in 1879 and then a year later in 1880 and began commercializing his incandescent light bulb, British inventors were demonstrating that electric light was possible with the arc lamp. In 1835, the first constant electric light was demonstrated, and for the next 40 years, scientists around the world worked on the incandescent lamp, tinkering with the filament, the part of the bulb that produces light when heated by an electrical current. The bulb's atmosphere, whether air is vacuumed out of the bulb or it is filled with an inert gas to prevent the filament from oxidizing and burning out. These early bulbs had extremely short lifespans, were too expensive to produce, or used too much energy. When Edison and his researchers at Menlo Park came onto the lighting scene, they focused on improving the filament, first testing carbon, then platinum, before finally returning to a carbon filament. By October 1879, Edison's team had produced a light bulb with a carbonized filament of uncoated cotton thread that could last for 14.5 hours. They continued to experiment with the filament until settling on one made from bamboo that gave Edison's lamps a lifetime of up to 1,200 hours. This filament became the standard for the Edison bulb for the next 10 years. Edison also made other improvements to the light bulb, including creating a better vacuum pump to fully remove the air from the bulb and developing the Edison screw, what is now the standard socket fittings for light bulbs. It goes on to talk about William Sawyer and Alban Man. Justice Swan, and discussion of patent law, copyright and patent law. Lovely. Skipping down. By the 1950s, researchers still had only figured out how to convert about 10% of the energy the incandescent bulb used into light and began to focus their energy on other lighting solutions. See, but I need to know about the concentrated arc. But they're moving on to fluorescent lights. Let's see. 1890s for fluorescence. 1920s and 30s, neon tubes. Fluorescent lamp research programs in the U.S. By the mid and late 1930s, American lighting companies were demonstrating fluorescent lights to the U.S. Navy and at the 1939 New York World's Fair. These lights lasted longer and were about 3 times more efficient than incandescent bulbs. The need for energy-efficient lighting, American war plants, led to the rapid adoption of fluorescence, and by 1951, more light in the U.S. was being produced by linear fluorescent lamps. There was another energy shortage, the 1973 oil crisis, that caused lighting engineers to develop a fluorescent bulb that could be used in residential applications. In 1974, the researchers at Sylvania started investigating how they could miniaturize the ballast and tuck it into the lamp. So the compact fluorescent bulb was developed in the 1970s. I guess I had not realized that. Interesting. And then LEDs. But it didn't talk about the concentrated arc. Rawr! I don't know. It just says, it mentions, I was working with Buckingham at the Western Union Lab when he was first developing the concentrated arc. So who is, well, okay, so Western Union, we've got that data point. So Western Union concentrated arc. And the first thing that comes up in a search is an eBay listing. But then there's a Smithsonian Institution item, concentrated arc lamp. Okay, I've got, this is the Smithsonian National Museum of American History, concentrated arc lamp. So let's see what the description says. There's no information. There's just a picture, but no information. Love it, love it. So it is a kind of lamp. No idea. Found it? Okay, Buckingham published in 1950 in the Society of Motion Picture and Television Engineers Journal. The open air concentrated arc lamp. This is a complete and total digression, and I'm here for it. I'm also rolling on a cord. There we go. The open-air concentrated arc lamp. Let's see what it says. We'll look at the abstract. The open-air concentrated arc lamp is a new form of the concentrated arc which operates in the open air and does not require any enclosing bulb or protective atmosphere. The light source is a sharply defined circular spot which is formed on the end of the electrode by a thin film of incandescent molten zirconium. The lamps can be operated from alternating or direct current and can be made in sizes up to several kilowatts. A 1 kilowatt lamp operating on alternating current draws 18 amps at 55 volts and produces 3,000 candle power from a spot 5.4 millimeters in diameter, whose average brightness is 130 cubic square millimeters. The radiation has a continuous black body type of spectral distribution and a constant color temperature of 3600 Kelvin due to a unique operating principle whereby the zirconium metal is constantly renewed from its own products of combustion. The lamps can have lives of several hundred hours. The exhaust products are non-toxic and the electrodes are replaceable. The lamp is characterized by extreme stability and ease of operation. It is expected to find application in projection, television, flood and spot lighting, and other fields which require intense light sources. So yeah, it would have definitely come in for theatrical lighting and film studios. High intensity lighting for research labs and film studios. Amazing. Thank you, P Squared, for locating that information. Okay, let's go back to some documents here. Anyway, it was one of those outstanding things from that first letter that I was just like, I need to know more. Okay, so who is this from? Early. E-A-R-L-E. Looks like it's Dr. Dr. Early Fowler, Sloan Physics Laboratory, Yale University. Let's see. I'm delighted that you are coming. ECF. Dear George, this is 8 November 1955. Thank you for your letter. I talked with Vernon Hughes and will expect you on the 15th of December. Plan to have lunch with me after your arrival at the physics department. I have 2 offices. Room B, Sloan Physics Lab, 217 Prospect Street, or room 501, Gibbs Laboratories just next door. Vernon and I wondered if we could post a shorter title than the one you suggest. Would you probably talk mostly about strange particles? Do you think strange particle production might do? We want you to choose your own subject, but do hope for a shorter title. Hope to see you soon. Perhaps we can talk it over. Best regards, Early. A shorter title could be Gamma Rays from Strange Particles. I will see you December 15th, if not before. Okay, great. I just know there's correspondence. I don't know. Now you recognize what they're working on? You prepared one? Excellent. Okay, let's see. Michigan physicists meet. I'm just... Are there any interesting dates in, like, the history of physics after 1952? And, you know, before 1993? Because the dates covered by this collection are 1952 to 1983, so it has to be within that date range. But are there any dates that I should maybe look and see if there's anything related or near those dates? Michigan physicists meet. An evening of physics consisting of coffee hour, dinner, physics exhibit, and talk on nuclear pile physics was held March 21st on the Western Michigan College campus. As was the case last year, it was sponsored jointly by the physics departments of Kalamazoo College and Western Michigan College. It was attended by physics major students and faculty from 6 other colleges and junior colleges. The physics exhibit following the dinner was partly modeled after the exhibit of novel devices held in conjunction with G.W. Stewart's University of Iowa Colloquium of college physicists every June. In this case, however, the competition was between undergraduate college students at the various schools instead of between the teachers. There were 13 exhibits this year. The winners were selected by a vote of those viewing the exhibit. First prize went to John Debris of Hope College for his diffusion cloud chamber. Second prize was awarded to Charles Kelly of Alma College for his apparatus for transmitting speech on a light beam. Fiber optics for audio transmission. The speaker of the evening was Frederick Laviolette of the Knowles Laboratory of the General Electric Company, who spoke on the subject, The Physics of the Nuclear Pile. About 125 attended the talk. Ralph O. Kermit, Kalamazoo College. Let's see. January 13th, 1956. Dear George, I have pleasant memories of our contact at the DePauw conference last spring. I was impressed by your friendliness, your understanding of the problems and achievements of the smaller physics departments, and by your willingness to cooperate with these departments in various ways. For the past 2 years, Kalamazoo College and Western Michigan College, both located in Kalamazoo, Michigan, have jointly sponsored an Evening of Physics sometime in the spring. I am enclosing a clipping from the May 1955 issue of Physics Today, describing our last evening of physics. Invitations are sent to all undergraduate college. Event brings together. Are they inviting him to talk, or? We would like to ask you to be our speaker this year. Speak on the same topic, growing out of your experiences with the Cosmotron, with the goal of making the talk an educational experience for undergraduate physics students. We are prepared to be fairly flexible concerning the date so that you can fit it into your schedule. Any Tuesday, Wednesday, or Thursday during March, except the 1st or the 27th, 28th, or 29th would be possible if you have no preference. I hope we soon receive an affirmative reply from you. Dear Professor Kermit, I regret very much that I'm not going to be able to accept the invitation. I would like very much to return to the Middle West and spend a day at a college where physics is being actively taught, as this is an aspect of my job here which I miss. The middle of March will find us faced with many problems centered around our new external proton beam and involving physicists from many universities. Much as I would like to come to Kalamazoo College, I have decided it would be unwise for me to do so. Thank you very much for thinking of me, and I hope to see you at a Physical Society meeting, or perhaps, even better, at another conference, such as the one held at DePauw last year. Aw, sad. The early 70s is when the current Stanford model of subatomic particles was worked out. I don't know if there's any fun correspondence about it, or if it would just be all math. Cosmotron was shut down in '66 and disassembled in '69. Ooh, yeah, we can head to the late 60s and see. I was just like, we're still in the like 1952 folder, which I'm not certain why this folder is labeled Correspondence 1952 and there are multiple 1956 letters in it. That seems like a problem in the processing. But yeah, let me see what I can find in like the 1960s era here. 1966. There's multiple folders for 66. Let's see what we can find. That last letter mentioned Physics Today, which I have never been a mathy person, but you may have noticed, I have an interest in space and science and stuff like this generally. And just because I have that interest, I have previously personally received Physics Today. Like, I used to have a subscription to Physics Today, which is a really cool magazine. I'm not good about reading magazine articles, so it was not economical for me to continue receiving that magazine because I'm not good about actually reading magazines. Deutsches Elektronensynchrotron. And that is completely not a German accent, and that is definitely German for the German electron synchrotron. Apparently this was located in Hamburg, and I apologize for butchering that. Yeah, Physics Today is a fun magazine. I subscribed to it because I thought it was an interesting magazine, and then I got a bunch of issues and never read them. And I was like, I need to not resubscribe because I don't actually read the magazine. It wasn't that I didn't want to, it's just, I don't know. I'm not good at reading magazine articles. August 24th, 1966. I wish there was a quick mute. That's one bad thing with this microphone, is I don't have a quick way to mute it. And I apparently swallowed wrong with swallowing the water. No judgment from me, Key Squared, about having a backlog of magazines. Let's see. This is from Lutz Kriege. Dear George, thank you very much for your letter of July 19 for the Thyratron specifications and for making EGG contact me about them. I have obtained prices and delivery times, and we are ready to purchase them once we have made up our minds to do so. I assume that Fisher's main reason to introduce these is the longer life compared with spark gaps, since we will be working with much lower event rates than you. I am not yet convinced whether we aren't better off feeding several planes with one little spark gap, EGG Model 17A, instead of every single one with a Thyratron. My question now is whether there are more reasons for preferring the Thyratron, like for instance, better spark characteristics coming out of the current limitation. Work is progressing very slowly here. On one hand, vacation time was inefficient. On the other, some unexpected delays occurred in the construction of the first big planes. We haven't been able to get a 70 centimeter by 100 centimeter printed sheet, although our local contractor has promised to deliver. Before that, he had gone on a 3 weeks vacation. Oh, geez. Fake foils, apart from the hardware, the whole group. What is a Thyratron? I think is the main question I have. Thank you, Key Squared, for answering the question before I even asked it out loud. A Thyratron is a high-power vacuum tube used in control systems. Let's see. Material written by Frank Turcott. Oh, it's a bibliography. Yeah, it's just a bibliography. We're going to skip that. Still used in equipment where more modern chips would get fried, like accelerators and big radio transmitters. Awesome. Ooh, American Institute of Physics. Oh. Yeah, that's just accounting stuff. Let's see. Salary of E. Walter Anderson. I recommend this person get a raise. Hey, that's nice. Monopole hunting. Let's see what this says. This is the Department of Physics at Harvard University from E.M. Purcell. Interestingly, apparently George was in Germany. The address, the letter was sent to George Collins in Hamburg. Dear George, thanks very much for your letter of January 13, which has received in me, which has revived in me pleasant thoughts about monopole hunting. I would certainly be glad to see an experiment mounted at SLAC and would be delighted to contribute in any way I could to the project. Your suggestion that this time the monopoles ought to be piped out to a low background region is very good. In fact, I should think that if one is this time reasonably generous with ampere turns, and in that environment, and with our previous experience, timidity would be easy to avoid, the experiment would be really very simple and reliable. The liquid-filled pipe we used to talk about surety could be made to make at least one bend without having any flux lines leak out. If one tapered the ampere turns in the coil so that they increased gradually from input to output, one could perhaps guarantee that the lines keep gently funneling inward down the pipe. Maybe some magnetic shield of larger diameter around the pipe would be good medicine. This time, too, one could avoid the slightly troublesome question of the possible accretion of molecules onto the monopole by stripping them with a foil before the last acceleration. If you want to go ahead, and if I could help in any way, count me in, but organize it exactly as you want to. In any case, I will certainly keep thinking about the experiment and will pass along any thoughts, useful or otherwise, that may occur. SLAC, Stanford Linear Accelerator in California. Can you clarify what a monopole is? I know that seems like a very basic question. So it seems like Collins was in Germany helping to set up another facility in 66. Huh. There's some names here. This one, simple letter, but name that we have encountered before. So this is the Institute for Advanced Study, Princeton, New Jersey. Dear George Collins, or Dr. George Collins. Dear George, thank you for your letters. We are delighted, of course, that you will talk at the Stony Brook Conference. You have always been on the speakers list. The tentative program that you received did not include your name because it only included those speakers who had accepted at the time that program was made. The curves that you sent me are extremely interesting. I am sure they will greatly contribute to the conference. Yours sincerely, C.N. Yang. C.N. Yang we have definitely encountered in the materials that we've been looking at during the high energy physics series. So even though just simple like, yes, of course, you're on the speakers list. Thank you for, it was the C.N. Yang signature that made me want to look at it. A particle with a single magnetic charge, that is a north with no south or vice versa. And so far we haven't found any. Interesting. Okay. Let's see. Third annual High Energy Physics Conference under the auspices of the Canadian Association of Physicists is to be held at McGill. Yeah, there's a lot of. This is just like all the correspondence. So this is finding the interesting ones is a bit more difficult. Ooh. These are telegram. Brookhaven National Laboratory, Upton, New York. 2. Dr. B.J. Moyer, Chairman, Department of Physics, University of California, Berkeley, California. AECGRNC. Let's see. Unclassified from George B. Collins. Mark Mandelkern worked with me last summer. I found him very intelligent, eager, and hardworking, with a good understanding of basic physics. His lack of judgment was no greater than expected from someone his age. Would rate his prospects for becoming an excellent physicist very high. I'm wondering if that's like a job application reference. Monopoles have been predicted by several theories, but there's no evidence they actually exist, unfortunately. Well, I mean, black holes were the same until we finally got a photograph of one. Like, they were predicted. The math said they should be there. But until we finally got a photograph of one, we couldn't say for sure whether they actually existed. Brookhaven National Laboratory, Upton, New York. Oh, this is another copy of the same thing. Are these all three the same? Yep. Interesting. If I had a specific intent in like searching for something, instead of just looking for anything that is interesting, like if I was doing research or something and looking for something specific, this might be more productive, but G.H. Vineyard, tenure of Frank Turcotte. Yeah, a lot of this is just like super mundane. I was hoping that there'd be more like science-y correspondence, but a lot of this is just more like academic correspondence. This is to invite you to come and speak. Trying to track that down leads you to find out there are two different Mark Mandelkerns. Amazing. Trying to see what jumps out. What says, hey, look at me, look at me. Mailing list. Report of foreign travel. High energy two-body reactions. Sort of paper there, huh? Travel plans. I know, like, sad. This is not what I was hoping to run into. I mean, it's fine. This folder, not super productive. That one's not even from George Collins. Yeah, I'm gonna put these papers back in the folder, and we're gonna pull out a different folder that will hopefully have some more science for us, instead of just, yes, I will come and speak at your conference, or we'd love to have you come and speak at our conference, which, you know, if you're trying to document his life and stuff like that, there's nothing wrong with those kinds of things. Those are useful. But for our purposes here today, less interesting. Let's see here. Sadly, they're all just like correspondence. This year, like, nomination for fellowship, annual reports by Collins Group, budget, justification schedules, climates of Virginia. Ooh. Oh, that could be, strangely, that could be interesting. Okay. I know, you're all like riveted by me flipping through. Ooh, 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 yes. Ooh, ooh, mm-hmm. I know, utterly riveting to have me looking at things and reacting to them, especially when they're things that you can't see. However, how about a couple of photographs to start here? Because photographs, undated. And yet, I'll take it. The question is, what are they photographs of? I think it's part of the cyclotron, but I don't know. I have the same photograph in black and white, but neither of them says what they are. Yeah. The sadness of an archival collection that has photographs that are unlabeled. Might be part of a particle detector control, but not certain. Yeah, I don't know. It looks really neat though. And then there's a picture of 3 people. And I believe one of these 3 people is George Collins. I believe. I think George Collins. It's hard to tell. Quite possibly the one in the bow tie. But I don't know who the others are. Well, and the distinctive feature that was visible in his other photo was the hook at the end of his nose, and they're all looking down, so you can't see that part of their noses. So I managed to find a folder of photographs, and the photographs ended up being less interesting than I had hoped. However, that doesn't mean there's nothing in here. I mean, there's plenty of interesting stuff in this collection. It's just skimming through all of the administrative paperwork was eating away at my ability to, or at my patience, I think is the word I want. Manuscript for 1992 speech at Notre Dame. I love it when I find speeches. I don't know what this person sounded like when they were speaking, but the beginning. I came here for the first time in 1935. That was a long time ago. What I found was a big room. It was perhaps 50 by 50 feet in area, perhaps 30 to 35 feet high, and it was empty. I had just visited the Department of sorry, I can't see what this, terrestrial magnetism. I had just visited the Department of Terrestrial Magnetism in Washington, where they had an open-air electrostatic generator with a top voltage of about 1 million. The empty room in the engineering building seemed just the spot for an even larger electrostatic generator, which would put us on the high-energy frontier of nuclear physics. This frontier was then a very few million electron volts. We decided on a machine with a 10-foot sphere supported on insulating columns near the center of this room, with a vacuum column extended into an adjacent room, also then vacant. All this eventually came about, but it would not have succeeded had it not been for support from the university's administration. Father O'Hara, who was then president. Father Bolger was head of the physics department. Father Steiner was dean of engineering, and there were, I am sure, other key members of the administration I have overlooked. This administration should be complimented for its daring, perception, and wisdom in supporting what must have appeared then as a harebrained enterprise. But support us they did. We were given money, perhaps $10,000, which was then a lot of money. And remember, there was no NSF or Department of Energy passing out federal money. I have always assumed this money came out of football receipts. The physics faculty was strengthened. From our standpoint, an important addition was Eugene Guth? I have no idea. There are possibilities of what those letters could be. A refugee from Vienna. Eugene had a personality that annoyed some people, but there was no question he was a very smart theoretical physicist who was a great help to our program. We had graduate students, good ones. Joe Feldmeyer, who is here today, was one of them, and there was Al Vitter, Al Schlefke, Vic Deiling, and others. But the most important addition to this group was Bernard Waldman. Bernard is not with us, and I am very sorry. He belongs here today. He was a pillar of strength. His contribution to the success of this enterprise was a major one. Eugene Guth. He was at Oak Ridge. Awesome. Thank you. I believe these were the first group of graduate students appointed to physics. What I am sure of is this handmade accelerator would never have been completed without them. Oh, that's cool. Let's see. Except that I don't think that last part was, yeah, major one. He was a very good friend of mine, and we worked well together. We both were burned with high-energy electrons. I like to think the remaining scars are medals of honor to both of us for dedication to physics at a time when the dangers of radiation were not appreciated. The building of this machine was a tour de force. Nothing could be purchased off the shelf. We had to design and build our own voltage measuring device, an electron gun, vacuum gauges, etc. It took real determination not to give up in the face of these obstacles. I will mention two major ones. The copper sheeting for the sphere was purchased as sheets of copper, which had to be hammered into a spherical shape to conform to the curvature of the 10-foot sphere. It was a boring task, which seemed endless. The vacuum tube was constructed of 6-inch diameter glass cylinders supported on a wooden beam. The something were placed end to end. The cylinders were placed end to end, and the front sealed with a special wax whose name I forget. I had a terrible time obtaining a degree of vacuum which would allow the electron beam to be accelerated. Unfortunately, O-rings had not been invented. I don't know if I might be able to get that. Aha, yes. I can do archives and stuff. And go. Thank you. This is really neat. Like, we were bombarded by high-energy electrons. Finally, everything worked, and we did physics. There were a couple of notes, like flip over here, and I sort of brushed past them. Let's see, a symbol of our close relationship in the arrangement, of course. Leaked. Oh no, what? What leaked? Oh yes, the cylinders placed end to end and then sealed with a sealing wax. This arrangement, of course, leaked. Let's see. Occasionally, we had fun. Sometimes, when the university had important visitors, we were asked to put on a demonstration. I would climb into the sphere and leave the entry door open. Someone else would turn on the charging bells? I don't know. While the visitors were standing around, but not too close. Soon, with a thunderous crash, a 20-foot shark would descend one of the legs while I was smiling at them out of the entry door. Concern for my welfare heightened the effect, and a frequent question was, "Are you sure there is not a paragraph in fine print in your textbook which makes this a dangerous experience for you?" Belt, got it. You built up an initial electric charge with a rotating belt. Got it, okay. I'm sorry, a 20-foot shark. It definitely says shark. Basically, they pranked visitors. Anyway, let's see. Finally, everything worked, and we did physics. We were the first to report nuclear disintegration by electrons. In our E's, it was beryllium we disintegrated. The threshold was found to be the same as for photons. Perhaps our best work was to verify the theory of Frank and Tam for the production of Cherenkov radiation. The angular production predicted by them was a mathematical formula that, let's see, is that cosine of, I'm going to say a thing and it's going to be wrong and I'm going to be embarrassed, but I think, is that cosine of theta equals 1 over, I am uncertain, BM of some sort. Yeah, but you're right. It did say shark. I don't know. I think they were doing pranks, but I don't know if that's theta. I honestly don't. But cosine of something, let's see, was confirmed, as was the radiation's predicted intensity. After all this work, it was gratifying to see our stature in the hierarchy of physics increase. Cherenkov radiation, the weird blue glow around accelerators and reactors from the emitted particles moving faster than they should through the surrounding medium. And it is a theta! Woo! Yay! I have no idea how I remembered or correctly identified that as theta. But let's see, Rabe came and gave us, we've heard of Rabe before, Robbie, I'm not sure. Came and gave us a speech. Maurice Goldhaber came to learn what we were doing. We've briefly mentioned Maurice Goldhaber on the stream before, but more because we were learning about Sulamith Goldhaber a couple months ago. And perhaps more important, our relations with the physics departments of neighboring universities were becoming quite close. You wouldn't have known it was a theta? I don't do math things either, but somehow I correctly identified it as theta. Oh my gosh, and hello, welcome in League of Whimsy. Hi, Eric, thank you so much for the raid. Rykar, thank you for the resubscription. Hi, Shadows of Life. I hope that you all had excellent fun with the Star Trek game. we're here today for Archival Adventures. I am Rogan27, also Anthony Wright de Hernandez. I'm the Community Collections Archivist here at Virginia Tech. And we're looking at the George Collins papers today. Collins was the director of the Cosmotron project at Brookhaven Laboratories in the 1950s. And later in life came and was a professor of physics here at Virginia Tech. And so we're looking at his papers today. And I'm reading through a speech that, what was the date on this? A speech from 1992 at Notre Dame, where he's talking about the first accelerator at Notre Dame that he worked on. It's been kind of interesting so far. But welcome in, everybody. It's great to have you here. Let's see. Talk given May 22nd at Notre Dame before the nuclear physics reunion. Aw. And actually, we just got to the end of that speech. Well, let's see what else we got. It was an interesting speech. I have a couple other interesting folders here. Computer-controlled systems. The resume and curriculum vitae of George Collins. I don't know that we're going to actually dive into the resume. I had thought that might be somewhat interesting, but at the moment, not terribly interested. Increasing the physics output of the AGS. Interpretation of highly inelastic proton-proton interactions. At 10, 20, and 30 BeV over C. I do not know what these mathematical items are. There's a proposal for an ISR at CERN. Ooh. We can look at that one. That might be interesting. It's all interesting. Proposal for ISR at CERN. I don't know what ISR is. I know what CERN is. Let's find out. This is dated 1971. Experimental proposal to the ISR at CERN to search for multi-gamma events from magnetic monopole pairs. George B. Collins, John R. Fichenek, and W. Peter Trower, apparently from their time, or his time here at TAG. The purpose of this experiment is to look for events that have associated with them multi-gamma rays with multiplicities too high to be attributed to known sources. Such multi-gamma events would, in the light of the explanation given by Rudderman and Zwanziger, be evidence for the existence of the Dirac magnetic monopole. Rudderman and Zwanziger point out that magnetic monopoles, if they exist, could hardly ever be created in a free state because the extremely strong and long-range attractive force experienced by a pair during their production results in the dissipation of most of the available energy as Bremsstrahlung. Before then, they can succeed in getting apart. I'm sorry, what is this word? Bremsstrahlung? Is anybody familiar? I'm going to look it up. I think we have looked this up before, but that doesn't mean I remember it. Bremsstrahlung, or breaking radiation, is the radiation given off by free electrons that are deflected, that is accelerated, in the electric fields of charged particles and the nuclei of atoms. it is not possible to predict the characteristics of the expected gamma rays because these depend on the unknown details of the production dynamics, of monopole mass coupling, etc. I love that this is like a partial piece of, oh, wow. Okay, so this is, at some point, they cut off the bottom of this piece of paper. They cut out part of what they had written and just pasted it onto another piece of paper because this is like the editing copy. The final copy they would photocopy and send that. And of course, now that it's aged a couple of decades, the glue has dried and has yellowed. Thankfully, it hasn't turned to chalky dust that's falling out yet. A good guess, however, is that both hard and soft gamma rays will be produced in profusion. Lower limits can be put on the multiplicity of photons using classical electrodynamics when the separation of the paired monopoles exceeds the range of nuclear forces. For soft photons, R and Z have made an analog between the radiation emitted during beta decay, the so-called inner Bremsstrahlung, and that from monopole pairs at R greater than R0, or R sub-zero, and predict multiplicities of the order of 10 squared at the center of mass energies on the order of those available at the ISR. Yeah. The mathematical bits of physics, my brain does not know enough. Additional hard gamma rays associated with the production process and additional soft ones associated with the decay of the bound system of monopolies will also exist. In all, R and Z predict that most of the center of mass energy going into monopole pair production will be converted into gamma rays, hard and soft. The key point in our preliminary search will be to detect multi-gamma events and to distinguish possible monopole gammas from multi-meson decay gamma rays on the basis of their different multiplicity distributions. Fortunately, we now know fairly well what to expect from pi. I don't know what that is. Is this neutral pi mesons? As a result of the cosmic ray experiment by L.W. Jones et al. I know we've seen that notation before. I think it's neutral charge pi mesons. The total charged multiplicity was found to average about 7, and to extend up to something like 14 for P minus P collisions at center of mass energies comparable to those at the ISR. Wow. Since the average number of positive pi plus negative pi might be expected to approximate the number of Y rays from neutral pi mesons, these distribution curves of Jones can be used directly to estimate neutral pi gammas. The expected multiplicity from monopoles is thus expected to exceed neutral pi gammas by an order of magnitude. That sentence had words in it, and I understood a lot of them. But I did not understand the paragraph. Like, there were words there, and I understand the definition of many of those words. That paragraph went way above my head. Wow. Detect multi-gamma events and distinguish monopoles from multi-meson decay. Okay. The details of how they're going to do that, way over my head. But they want to run an experiment to distinguish between predicted monopoles and multi-meson decay. Hi, 123 Ricardo 210. It all sounds very sciencey and smart, and I really wish I'd done physics for a few years more. I have only had high school physics. Like, that is all I've had, high school physics, and I once subscribed to Physics Today. Beyond that, not. There's too much math in physics for me. And anyway, it's really interesting stuff. Like, even though I don't really understand most of when they're getting into like the details of here's how we're going to do this, it is quite interesting. Ooh, short form. Trying to figure out how to tell if things we're detecting are magnetic monopoles or are something else we already know about. By looking at how quickly they spread out, you can figure out where they came from and how fast and heavy they are. Sort of. You also had just high school, although a Dutch one. Decent as well until the math showed up. Yeah. Oh, that makes me feel better, Key Squared, that you have a degree in physics and still can't follow all the details. That makes me feel much better. Yeah, this is. I've really been enjoying like the end of the month high energy physics focus for the stream. Sadly, I am almost 10 minutes over my time, so I do need to like move us towards end of stream. I knew that if Eric ended up bringing people over today, it would be right at the end, because I knew Eric was planning to go long today. I actually had entertained the notion that I might raid him for once. But coming up next week, I do want to just mention what next week's stream is. I just have to find it real quick, because I forgot. Oh, hi, Galara. Welcome back. Thank you for the resubscription. Amok. Let me look. I just can't remember, because it's like 2 weeks ago that I last looked at whatever we're doing next week. Let's see. Next week I have Paul Hill. What do I remember about the Paul Hill collection? Ooh, oh yes. I have titled next week's episode Space Stations and Interstellar Travel, the Paul R. Hill collection. So it is really neat. It's a bunch of papers about work that was done at NASA Langley to build prototypes of space stations and also experiments towards interstellar travel. So next week should be some pretty good content. Oh, I'm sorry that you're gonna miss it, Key Squared. If you do manage to make it, that'll be rad, but otherwise, yeah, the VOD will be available. Sounds exactly like what your inner 7-year-old would die for. Yeah, it looked really cool. I had a lot of fun just like flipping through it and jotting down like the things that stuck out to me as really interesting. So hopefully I will see some of you back next week as we explore some like 1950s era space station design and interstellar travel scientific research. So that is going to be next week. Let me go ahead and figure out where we're going to pop for a raid. I don't know. We could do. There's always the aquarium. I think Steven is on doing Power Wash. Oh dear. Yeah, no, we're gonna head on over to the Monterey Bay Aquarium today. Their stream today, celebrate World Otter Day with the Otter Cam. So we're gonna pop on over there for World Otter Day, because that sounds like a heck ton of fun. But yeah, thank you everybody very much for joining me. I hope that I see you all again soon for another Archival Adventures. I've got 2 more episodes before I'm taking a month off. So 2 episodes in June, and then the next one will be the last week of July, where we'll do another high energy physics focused one. So hopefully I see you for one of those soon, and episodes in the future. Until I do, keep exploring history, everybody.